Okay, so get this. Today, we're going to be like AI engineers, but instead of building the thing, we're going to reverse engineer it. We're talking neural networks, people.
Yeah, the stuff of science fiction, except not so much anymore.
Right. I mean, these things can recognize your face, translate languages on the fly.
Predict the stock market, even.
Wild. So we've got a stack of articles and research lined up all about how these AI marvels actually work. And trust me, by the time we're done with this deep dive, you'll see neural networks in a whole new light. Guaranteed.
It all starts with a pretty simple, elegant idea, actually.
Yeah.
Mimicking the human brain. Imagine, if you will, a network of interconnected nodes, and each one is kind of like a tiny neuron firing off signals. That's the basic blueprint of a neural network.
So we're basically peeking under the hood of intelligence itself. I am so in. But how do we even begin to teach a network of like digital neurons to think? I saw one of your sources mention training a dog, actually.
Perfect analogy. It really helps to make this stuff click. So picture this. You're trying to teach your dog a brand new trick.
Yeah.
Right? Every time you give them a command, that's like feeding data into the neural network.
Okay, I think I'm following.
And then the dog's action, whether it's nailing a perfect set or, making a beeline for the nearest squirrel.
Or the mailman.
Exactly. That's the network's output, right? It's prediction based on the data it got.
Gotcha. So far, so good. But how does the dog actually learn? Like, that's where the real magic happens, yeah.
You're telling me. And that's where things get really interesting with neural networks, too. If the dog gets it right, awesome. But when they mess up, and that's your cue to adjust your training. Maybe you didn't use the right tone. Maybe there were too many distractions. This whole feedback loop, constantly refining your approach, that is the key to how neural networks learn.
Okay, so instead of scolding our AI for chasing digital squirrels, we need a more, shall we say, mathematical approach.
You got it. Neural networks learn through two fundamental processes. We call them forward propagation and backward propagation. Sounds kind of intimidating, but bear with me. It's actually really elegant when you break it down.
Hit me with it.
So, forward propagation. That's like the dog hearing your command and making its best guess about what to do, right? Then backward propagation kicks in that's analyzing the outcome. Good sit or squirrel fiasco. And it uses that information to adjust how the network itself is set up.
Hold up, settings? Like, are we talking about literally going in there with a tiny screwdriver for AI brains? What does that even look like?
Well, not a screwdriver exactly, but you're on the right track. See, those connections between all those digital neurons we talked about, each one has a weight assigned to it. You can think of them kind of like dials that control how strongly one neuron's signal influences the next one.
I think I see where you're going with this. So if the dog chases the squirrel instead of sitting pretty, we're going to go in there and tweak those dials to try and get a different outcome next time, right?
Bingo! And that, my friend, is exactly what backward propagation does. It figures out which dials need adjusting and by how much to make the whole network more accurate. It's like fine-tuning a really, really complex machine. Except instead of gears and cogs, we're dealing with algorithms and data.
This is awesome. Okay, so we've got our dog as neural network, and we're tweaking those imaginary dials. But before we get too deep into this whole training montage, let's zoom in on the neural network itself. What's actually going on inside that AI brain of ours?
Picture a network with different layers, kind of like a relay race, actually.
Yeah.
First up, the input layer. That's where the data enters the system.
Makes sense.
Sticking with our image recognition example, this is where we feed in the image, pixel by pixel. Then we've got the hidden layers.
Hidden like secret agents of AI. I like it.
Kind of. This is where the real magic happens, actually. Each hidden layer takes the info that the layer before it passed on. It processes it, transforms it, then sends it along to the next layer, like a chain reaction.
Okay, so like a game of telephone. But instead of whispers getting all garbled, we're actually building up to something amazing, right?
Exactly. Each neuron in these layers, it's making decisions, basically. And it's using those weighted connections we were talking about before to do it. Like, is this image starting to look more like a cat or more like a dog? Those weights, they're what guide the network toward the right answer.
Okay, so we go input layer, then through the hidden layers. What happens next? What's the grand finale?
Output layer. This is where it all comes together. This layer takes all the processed info, after it's been passed through all those hidden layers, all those neurons firing, and spits out a prediction. Cat, dog, whatever it's learned to identify.
Let me see if I got this straight. So forward propagation, that's like the neural network's first attempt at the trick, right? The initial woof when you ask for a bark. It takes the input, that image, in our example, runs it through all those layers, all those weighted connections. and then makes his best guess.
You got it. But here's the thing. What makes this whole system truly intelligent is its ability to learn from its mistakes.
To realize that the woof wasn't quite a bark yet.
Exactly.
And that, my friend, brings us right back to backward propagation, that all-important feedback loop. So how does it actually do that? Analyze its mistakes, I mean.
This is where it gets really, really clever. Remember those weights, those like dials controlling the connections between neurons?
Yep, got them.
Backward propagation. It's all about figuring out how to tweak those dials to make the whole network more accurate.
Okay, I'm with you so far. So let's say our AI sees a picture of a, like, adorable, fluffy kitten, right?
Right.
But it guesses dog. How does it know it messed up?
It calculates something. We call it loss, but basically it's a measure of how far off its prediction was from the actual correct answer.
So a big difference between dog and cat means there's a lot to learn, right?
Big time.
So this loss, this
Yeah.
measure of being wrong, that's what triggers the whole backward journey through the network, like a backtrack button for AI.
Exactly. That's the signal. And the network uses this loss to figure out how much each of those little weights contributed to the error. Like, imagine trying to find your way out of a maze every time you hit a dead end. You learn something about the paths you shouldn't have taken, right?
Okay, that makes sense. So it's retracing its steps, figuring out which turns led it astray so it can avoid them in the future. But how does it even know which turns were wrong? What's guiding it?
Gradients. It's a bit of a heady concept, but think of a gradient like a compass needle, pointing the network toward the right answer. A strong gradient means a big course correction is needed.
Ooh, like, whoa, that weight over there, that's what really threw me off. I need to adjust that dial significantly.
Exactly. You're getting it. And to actually guide these weight adjustments, the network relies on some pretty clever algorithms. Gradient descent is one. Well, imagine you're trying to find the lowest point in a valley, right?
Yeah.
You might take small steps, always heading downhill.
Following the slope.
Yeah, exactly. That's kind of what gradient descent does. It takes small steps, always following the gradients, until it reaches the minimum error, like the bottom of the valley.
So the network has like a built-in system to find the best possible settings. Just like you might fine-tune a recipe to get it just right, only instead of sugar and flour, we're dealing with weights and biases, right?
Perfect analogy. And here's the kicker, this whole process, forward propagation, backward propagation, weight adjustment, it happens over and over and over again.
No kidding.
With every single image the network processes, this continuous cycle of prediction, analysis, refinement, it's how the network gets better over time.
So the more data we feed into the network, in our example, images, the more chances it has to learn and improve and get those dials just right.
Precisely. It's all about practice, just like with any skill. The more it sees, the better it gets at recognizing, well, anything, really.
This is blowing my mind. It's like we've uncovered the secret language of AI learning. But you mentioned earlier, all of this actually connects back to us, to the way our own brains work. Is that connection? Is it more than just a metaphor? Or
It's definitely more than just a metaphor, but it's not a perfect one-to-one match either.
okay, how so?
Well, neural networks, they're inspired by the brain, for sure, the way they're structured, how they process information.
Right.
But our brains, they're still in a whole other league when it comes to, like, raw power and efficiency.
So what you're saying is our brains are still the ultimate learning machines, at least for now.
For now, definitely. Think
Yeah.
about it. You can show a kid a picture of, say, a cat and a dog, just one picture, and they can probably tell you which is which, even if they've never seen those exact breeds before.
True, it's like instant recognition.
Right. But a neural network, it might need to be trained on, like, thousands, maybe even millions of images to get to that same level.
Wow, that really puts things in perspective.
Yeah, our brains are incredibly adaptable. We can learn from just a few examples, and then boom, we could apply that knowledge to totally new situations. AI systems are getting better at this, that whole generalization thing.
Yeah.
But they're still playing catch-up, big time.
Okay, I'm starting to get the bigger picture here. We've got these crazy, powerful AI systems. They can do these incredible things, but they're still, like, in their early stages, right? Kind of like the AI equivalent of us learning our ABCs.
Exactly. Still a lot of room to grow. But this whole forward and backward propagation thing, that's the engine driving their evolution, basically. It's what's pushing them toward that human-level understanding that we're talking about.
So it's not just about, like, recognizing cats and dogs anymore, is it? I mean, you were saying before.
Oh, no, not at all. This stuff, it's already everywhere. You've probably used it yourself a dozen times today and didn't even realize it. Unlocking your phone with your face.
Oh, yeah, every day.
Personalized recommendations, like for a new song you might like or a movie.
Yep, guilty as charged.
Even your navigation app, figuring out the fastest way to get you home. It's all powered by this
Well,
stuff.
okay, when you put it like that, it's clear this isn't just some like abstract concept anymore. It's literally changing how we live our lives.
It really is.
But all those examples, face recognition, recommendations, all that, they all rely on the network being able to see those images, right? Like to actually understand what it's looking at. How does it even do that? What's going on inside those hidden layers that lets AI tell the difference between, say, a cat and a dog, or even a golden retriever and a German shepherd?
$1 million question. That gets to the heart of one of the biggest challenges in AI right now, actually. Interpretability. Yeah, like we understand the mechanics of how these networks learn, the forward propagation, backward propagation, all that.
Right.
But actually peering inside those hidden layers,
Yeah.
figuring out what features the network is zeroing in on to make its decision,
Yeah.
that's still kind of a mystery.
So like the network's developed its own language for understanding the world, and we're still working on cracking the code.
Pretty much. But researchers, they're making progress all the time. And the more we can figure out about how these networks think, the more it could change things.
Yeah, I bet.
And not just for AI either. I mean, this could have huge implications for how we understand our own intelligence.
Now, that is an exciting thought. Well, we have journeyed deep into the heart of neural networks today. We've talked about the whole intricate dance of forward and backward propagation, the algorithms that make it all tick.
And how it's changing the world already.
Exactly. It's been quite a ride. So, any final words of wisdom for our listeners today before we wrap things up?
I'd say next time you come across some AI, right? Whether it's a chatbot, some kind of recommendation engine, maybe you're even in a self-driving car.
The future is now.
Right, just take a second. Think about the incredible complexity that's happening behind the scenes. These systems, they might seem magical, and they kind of are, but really they're the result of decades of research, tons of work, and those elegant principles we were talking about, forward and backward propagation. It's honestly a testament to human ingenuity, and our drive to understand the world around us, even as that world becomes more and more digital.
Beautifully put. And to our listeners, we hope this deep dive has left you with not just a better understanding of neural networks, but a sense of awe at what they can do, because this is just the beginning, folks.